All. This is M.Danial Shabir. Welcome to the show. Today, the topic of our discussion or concern is the acetylcholine. That is acetylcholine is a vasodilator. So this is the question. So there are two answers of this question. First one, yes, acetylcholine is a vasodilator only when we administer the acetylcholine from the external source. This is the first answer. The second answer is that acetylcholine is not a vasodilator. Why? Because as we know, acetylcholine basically is the neurotransmitter of the parasympathetic nervous system. Parasympathetic nervous system, PSN. And our blood vessels are not innervated by parasympathetic nervous system. So the takeaway of the discussion is that if we administer the acetylcholine from the external source, then it will be a vasodilator. And as an endogenous substance, it is not a vasodilator. Now we will see the molecular mechanics of the acetylcholine, that how acetylcholine causes the vasodilation. So let's suppose this is the endothelium of the blood vessel and this is the smooth muscle. Let's suppose this is the acetylcholine. Acetylcholine, which we administered from the external source, activate the M3 receptors. M3 receptor, which are present on the endothelium of the blood vessel. So these are the M3 receptors. So when acetylcholine activates the M3 receptors, these M3 receptors are coupled with the J protein. And this J protein then will activate this PLC, phospholipase C. And this phospholipase C basically a cutter. It acts like a scissor and it converts this PIP to phosphatidyl inositol diphosphate, which is basically a long chain fatty acid. It is converted into IP3 and DAG. IP3 mean inositol triphosphate and DAG mean diacylglycerol. And the IP3, which is generated into the endothelium, now activate the IP3 receptors, and these receptors are present on the surface of the ER, endoplasmic reticulum. As we know, endoplasmic reticulum is the rich source of the calcium. So when this IP3 activates its receptor, which are also known as ryanodine receptors, so the calcium level rises into the endothelium of the blood vessel. So this is the calcium and this is also the calcium. This calcium then will activate the calcineurin, which is a molecule which is present into the endothelium of the blood vessel. And this calcineurin then activates NF80. And this NF80 then will open up the gene. Which gene? The gene which is responsible for the production of ENOS. And what is ENOS? Basically, ENOS is an enzyme and it is abbreviated as endothelial nitric oxide synthase. And this endothelial nitric oxide then converts the L-arginine, which is basically an amino acid, into the nitric oxide and citrulline, which is an other amino acid. So this is the first pathway, and the second pathway is the calcium. This one, calcium, bind with the calmodulin, and calmodulin is basically a protein which is present into the smooth muscle, and it is the counterpart of troponin which is present into the myocytes. And then this endothelial nitric oxide is activated by calcium and calmodulin complex. First pathway is that it is being formed by the NFAT, and the second one, it is activated by calcium and calmodulin complex. And now this endothelial nitric oxide synthase then will convert the arginine into the nitric oxide and citrulline, as we have discussed before. So the nitric oxide, which is basically generated into the endothelium of the blood vessel, will perform two function. And this is the smooth muscle of the blood vessel, this one. And as we know, the smooth muscle of the blood vessel have these potassium channels, and the nitric oxide, which is generated from the endothelium, now will activate the potassium channel, and these potassium channels will be activated. And as we know, potassium always enrich into the always rich in intercellularly, and when the potassium channel will be activated, the potassium will go outside of the cell, and it will leads to the hyperpolarization, and this hyperpolarization then leads to the vasodilation, or the dilation of the blood vessels. So this is the first mechanism of nitric oxide, that how nitric oxide dilates the blood vessel. So we will see the next, or the second pathway. So the nitric oxide also activates the guanylyl cyclase. It is basically an enzyme, and this guanylyl cyclase will convert the GTP into the cyclic GMP, and this cyclic GMP then will activate protein kinase G, which is also present into the smooth muscle of the blood vessel, and this protein kinase G then will causes the phosphorylation of the myosin light chain kinase. And what is the normal function of the myosin light chain kinase? The normal function of the myosin light chain kinase is that it causes the phosphorylation, means it attaches the phosphate onto the head of the myosin. When this phosphate is added onto the head of the myosin head, there is the bridge formation between actin and myosin, and there is the contraction of the smooth muscle. But no, when this protein kinase G will cause the phosphorylation of the myosin light chain kinase, basically it is an enzyme, and when it is being phosphorylated, it got activated, deactivated. Please do remember this. When protein kinase G will causes the phosphorylation of myosin light chain kinase, it got deactivated, and when it will go deactivated, it will not be able to cause the phosphorylation of the myosin light chain head, and when myosin light chain head will not be phosphorylated, there will be the passive vasodilation, because there is the no phosphorylation of myosin head. So in this way, the blood vessels are dilated. So this is the today's discussion. If you wanted to support me, please do me a favor. Please like, subscribe, and share, and please press the bell icon. Thank you very much.